Welcome to the Metaverse Standards Forum, special session of the Standards Organization, special session number 3, towards interoperable anchoring for XR. We'll have two presenters today, Jérémy Lacoche from Orange and Jérôme Royan from BCom. It is now just a few minutes after 7 in the morning in West Coast time on the 30th of April, 2025. These sessions are organized and produced by Thomas Stockhammer, Christine Perret, and Leonard Daly. Today's agenda is the presentation towards interoperable anchoring for XR. It's work by ETSI and the Augmented Reality Foundation Augmented Reality Framework by Jérémy and Jérôme. They will have Q&A afterwards, and there's also a survey to conclude where you can enter your comments in on what you thought went well or did not go well and should be improved. So we have a special guest today, Neil Trevitt, the president of Metaverse Standards Forum, who will give us a short introduction to the organization.
Yeah, thank you, Leonard. So we just wanted to take a minute or two just to introduce the forum whilst folks are gathering. So we have just a couple slides here. So let me explain what the forum is about if this is your first contact with us. So many agree that the metaverse is going to combine the connectivity of the web with the immersiveness of spatial computing, and this means we're going to be bringing together multiple potentially disruptive technologies for really a generational shift in how we interact with our technology and each other, and it's this shift that we're calling the metaverse. And these are diverse technologies. It's AI, GPUs, XR, Web3, networking. And in particular, we think that the metaverse and AI are deeply symbiotic. The metaverse increasingly becoming the user interface to AI-driven compute resources and smart agents. So because we're bringing together these multiple evolving technologies, it's really impossible to predict how the metaverse is going to evolve. But the one thing we do know is we're going to need interoperability between multiple technologies at a global scale, which means we're going to need really timely interoperability standards. And that means we need standards organizations to address these real-world use cases and requirements. And indeed, the scope of the potential metaverse is going to require a constellation of open standards through creation by hundreds of standards organizations, consortia, nonprofits, companies, and universities all cooperating together. And that was really the catalyst for the formation of the forum, which is not a standards organization itself, but it's a pretty unique, neutral venue, and it's open to all. And it exists to encourage cross-silo communication and cooperation between the standards community and the wider industry. So you can go to the next slide, Leonard. So the forum is a non-profit organization. We've attracted over 2,600 organizational members to assist and accelerate the development of needed standards by providing industry input and visibility to standards organizations. We undertake pre-standardization activities, including use case generation, requirements generation, draft specification feedback, identification of standardization gaps and opportunities for standards organizations to leverage and align with each other's work. We also try to do post-standardization activities, including testing interoperability, creating tooling and educational materials on how to effectively use the standards once they're deployed. The forum is very pragmatic, we try to be, and driven by bottom-up industry priorities to help solve today's most acute interoperability pain points. We've avoided trying to define the metaverse or create a long-term metaverse roadmap, as we think things are going to evolve in a very Darwinian way. But if we do believe that ongoing innovation is going to create this wave front of immediate opportunity on the road to an eventual metaverse platform. Next slide, please, Leonard. Thanks. So the forum organizes into multiple member-driven domain groups, each focusing on a particular aspect of standardization. ranging from topics like interoperable 3D assets and avatars and volumetric media, XR, and virtual world integration, which is going to be the topic for today, networking technologies, the web stack as it evolves, spatial computing capabilities, Web3, including management of digital rights and identity, including privacy and security, and use cases such as the industrial metaverse. So if members see the need for standards cooperation around additional domains, they are warmly encouraged to initiate new domain groups through the forum's well-established exploratory group process. And central to much of the forum's domain group activity is a standards register working group that maps standardization activity throughout the industry and collects and collates use case and common vocabulary from across the other domain groups. So next slide. So that was a brief introduction to the forum. We try hard to be a welcoming and pragmatic organization, open to all, and fostering meaningful interoperability cooperation to help the spatial evolution of the web. So if your organization is not already a member, please do join for full participation in all our domain groups. There's no cost, no patent licensing, not even an NDA. Everything here is public. We do, though, appreciate the support of our principal members that do pay a membership fee to support the forum's activities, and in return, they gain a chance to participate in forum leadership. So next slide. So that brings us to today. And one way the forum drives visibility and feedback for standards organizations is to provide them an opportunity to inform forum membership and the wider industry on their activities and to get hopefully useful feedback via these special SDO sessions. All SDOs are welcome to encourage to request a session. And if you're interested, please reach out now at the link on this slide. And today we're very fortunate to have Jérémy and Jérôme, who are going to be updating us on ETSI's standardization activities in XR. So welcome, Jérémy and Jérôme. Thank you for taking the time to present to us today. We look forward to learning about your activities and hopefully providing you useful feedback and cooperative opportunities. Thank you.
Thank you.
So today's agenda will have the presentation. It'll be in 3 parts. You can see on the screen, followed by a Q&A. Certainly immediate questions can be handled during the presentation, and then we'll conclude with surveys and thank yous. So today's presentation towards interoperable anchoring for XR registers, or augmented reality registers AR assets in 3D with the real world in real time. To achieve this, an AR system estimates the 3D transformation of an AR device in relation to the real world objects, or conversely, based on its different sensors. This presentation will present the ETSI ARF augmented reality framework standardized architecture for AR systems and the recently published specifications and available tools for providing a world representation and performing pose estimation on various AR devices. Pose estimation is achieved by combining the world representation with data from the device sensors and can be conducted locally or in a remote computing platform. The presenters are Jérémy Lacoche. He is a research scientist at Orange, specializing in the convergence of XR, AI, and digital twin technologies to develop advanced interactive tools for augmented technicians. He is the current chair of the ISG Augmented Reality Framework at ETSI, where he contributes to establishing a standardized and interoperable architecture for AR system. Jérôme Royan is a senior scientist, deputy director on strategy, performance, and innovation at IRT BCom, focusing on spatial computing, XR, AI, and digital twins. He is responsible for the technical and scientific development of BCom's Overview, a remote visual positioning and 3D reconstruction platform for industry. He is the current vice chair of the ISG Augmented Reality Framework at ETSI, where he contributes to establishing a standardized and interoperable architecture for AI systems. Please welcome Jérémy and Jérôme.
Thanks a lot for the introduction.
So first of all, thank you all for your invitation to let us present the result of the activity achieved at the ETSI Augmented Reality Framework Industry Specification Group. And we'll present to you today our work on improving the interoperability for XR system, on more specifically for XR anchoring. So we'll have different sessions. Can you move to the next slide, please? Yes, we'll first start to introduce the AR, how it works, how you can, for example, estimate the pose, what was previously presented, what are the limitations of existing AR standards, and we will let you, for more dynamic session, let you ask some question if you want. We'll try to answer it. We'll have a second part concerning the specification of the ETSI Augmented Reality framework, and we'll provide you some examples showing how you can use the specification. And we will finish with the available tools that are that you can use to integrate this specification in your existing solution and technologies. So what we consider as an augmented reality system, for that, we mainly use the definition of Azuma that explains that an augmented reality system is the ability to mix in real time spatially registered digital content with the real world. So if you can have a look to the figure on the right, it both combines real and virtual world. It is a system that is interactive in real time and that provides some 3D illustration. If you do not have 3D illustration, we can consider it much more as a compositing system or an head-up display. This is what you can see in this image, where you can display on the screen of a car. You can display the speed, but the speed is not really attached to a specific element of the real world. It just displays on a local reference of the frame of the car. If there is no real-time interaction, we call that special effects. That's the case of movies such as Jurassic Park, where you have both a combination of real and virtual content. It's registered in 3D. You can see that the dinosaurs is well positioned according to the car behind, but it's not interactive. Everything is pre-computed. And finally, when you have no combination of real and virtual reality, but only virtual content, we are speaking about virtual reality here. And you know that, everyone knows that. So what we consider as an augmented reality system is really a combination of these three characteristics, what you can see in the center. So for example, here, you have some instruction for a maintenance task where you see the different arrow perfectly positioned according to the real system and display in AR. So to obtain this 3D illustration, you can see on the right in this video where you see a kind of mascot, a robot, display exactly at a perfect position according to a real image that is in the real scene. What you need to do, you need to estimate the pose. The pose is the position orientation of, for example, here the camera, or more generally of the AR device. And if you align the viewpoint on the virtual scene with the viewpoint of the camera, you can after combine both virtual and real content, the virtual content with the video, and it will seems to be perfectly aligned or registered in 3D. So all existing AR systems today have to estimate the pose of the AR device, and this is one of the main features that an augmented reality device have to provide to experiment augmented reality. So how we can estimate the AR device pose? What you need first is a 3D representation of the real world. And you need some sensor. And this sensor will capture the world, but you will have to combine both a representation of the real world with different kind of sensor. You can have one-dimension sensor, what you can see on the left here. This is typically a GNSS or a localization based on ultra-wideband or Wi-Fi, where you will have emitter cells, for example, that will emit a specific signal captured by the sensor. But for that, and to estimate the pose of the sensor, you need to know the position, for example, of the different cells or emitter. In the case of a 2D dimension sensor, you need to have a 3D representation such as a point cloud, a fiduciary marker, an image marker. You need to have this 3D representation of the real world. You will capture this knowledge with a camera, and you will try after to match some feature in your image with some elements of your representation of the real world. And this is the same for 3D dimension sensor, where you can use some depth sensor on LiDAR that provide you some depth map. But again, you will try to match or to fit this depth map with a 3D representation of the real world. So in any case, and you can just click once, what you need to estimate the pose is you need a 3D real world representation. And this is one of the main focus of our activity at ETSI industry specification group called Augmented Reality Framework. So what's happened today in terms of lack of interoperability is that there is no real common representation of this real world. You have different way to represent the world depending on the ecosystem. What is the limitation of this lack of interoperability is that when you are using a device from one ecosystem, you cannot provide a localization or estimate the pose based on the representation of a second ecosystem, a world representation. It means that you need to create world representation for each ecosystem if you want to use different kind of device in your environment. What is a main limitation, for example, for industry, where sometimes for specific tasks, you prefer to have a tablet or smartphone or 2D screen. And for other tasks, you need to have free hand and you prefer to use some AR glasses. And what's happened is that industry need to duplicate the representation of their factories or of their environment for each ecosystem. What we expect with better interoperability is to have a unique world representation that can be used by any kind of devices, whatever the ecosystems they are using. And just keep up to date a unique world representation. So this is one of the main objectives of this group to provide a unique world representation. So for example, there is what we call spatial anchors. You know, all of you know them. But you have again different kind of representation for spatial anchors. You have different kind of proprietary formats. Each ecosystem has its own way to manage spatial anchor with their own platform, so there is no real interoperability. And most of the time, it's based on a point cloud behind to be able to localize different AR system based on their camera. But you have other kind of what we call, and you will see that just after, trackable. You can imagine to have some images or to use meshes or a CAD representation of the real world, and to use this representation to be able to estimate the pose of the AR device. And all these trackable are not implemented by all ecosystems. And moreover, sometimes there is a lack of camera access that really prevent developers from implementing the pose estimation based on these kind of trackables that are not available on these different ecosystems. Another point concerning the lack of interoperability is the fact that it's not so easy to share a world representation between different kind of application. Most of the time, when you are developing an application in AR, you will create a world representation, for example, a 3D map or a spatial anchor dedicated to your application. That's not so efficient. If you have, and if you click, please, Jérémy, if you have something that it's much more interoperable, you can imagine to have a single world representation that can be used for many kinds of application. Imagine, for example, for a city, you have a world representation of a city, and you can share this world representation to develop many kinds of application for this city. It's the same for industry. You have a world representation of a factory, And you can imagine to develop on top of that many kind of application for security, for maintenance aids, for many, many other applications. Again, you don't need to have different spatial anchors or workstation for each application, but just having once a single workstation where you can develop many kind of application on top of that. Another point is that today, when you are using trackables, it's not the case for all AR systems, but for many of them, these trackables are covering a quite small area. Most of the time, it's quite difficult to be able to develop AR application at the scale of a very large scale, the scale of a building, the scale of a city. Most of the time, you are limiting to the scale of an object or at room scale. What is interesting is that if you are combining different kind of trackable and you spatially structure them, you can imagine really to address a very large scale AR application. And we will show that just after in the kind of examples that can be developed based on our specification. Please,
Okay.
I will let you the floor, Jérémy.
Yeah, I can go on. And so when looking at existing standards today, there is no one really addressing this kind of XR world representation. So for example, when you look on the Chronos side, we have OpenXR, which provides the unified interface for developers to create immersive experiences across various hardware and software platforms. So it indeed allows access to the pose of the devices, as well as the access to more advanced tracking features such as image trackable and spatial anchors for the use of vendor extension. So it's then able to deal with anchoring augmented reality content at runtime, but it does not really provide an offline mode to create, store, and share a world representation that could be used on several applications and devices. So to continue, we have, of course, OpenVX, which provide hardware-accelerated computer vision APIs that can be really useful to boost the performances of localization systems if you want to develop your own. But as well, it does not manage the representation of the real world. And so to continue, regarding Chronos, we have also GLTF, which is, of course, the file format for transmitting 3D models and scenes. And for some extension that have been proposed at MPEG in the context of the Scene Description Working Group, it is able to manage anchoring to the real world by using trackables and anchor nodes. So it can, for example, deal with image markers, mesh tracking, or spatial anchors, such as the one managed by HoloLens or AirCore. So here, this anchoring description is directly linked to the virtual scene and is not an independent representation that can be shared across immersive experiences. And so to continue, when we look at OGC, they of course propose OGC GeoPose for handling geographical frame of reference, but they are not providing this kind of information about trackables that are essential for estimating the pose of augmented reality devices, for example, based on computer vision systems. On the OGC side, there is also ARML 2.0. So as GLTF with MPEG anchoring extension, they are much more focusing on AR assets and anchors, but not on the world representation. So for example, it includes something called image targets to link an asset to an image trackable. And directly linked with GeoPose, we have something called OSCP GeoPose protocol, which is developed between OGC and OpenAir Cloud Consortium. So it proposes an API for visual localization. So basically, you will share your local sensor data, such as images, GPS data, and you will retrieve from a server a GeoPose from a visual positioning system. So here there is not a real abstraction of the representation of the real world, but a way to ask for a pose in a non-referential, which can be, for example, a terrestrial reference frame. So this solution is particularly interesting and discussed a lot in the real virtual world integration working group at MSF. And it also comes with open source initiatives. So both GeoPose and OSCP GeoPose protocol can be seen as complementary of what we have been proposed at ETSI. And so to finish with existing standard, we have also some work done at MPEG with GPCC and VPCC for compression of 3D point clouds. So indeed, 3D point cloud is one way of representing the real world, in particular for SLAM algorithm. But in that case, GPCC and VPCC will need to be extended to associate points with metadata called descriptor in such algorithm. And last, you have also MPEG-V, which is quite old and that has not been particularly adopted. It is also a standard for interoperability between real and virtual worlds. So before moving to the description of the ETSI specification regarding world representation, we can have some time for question and discussion if you want. For example, it can be interesting to see if some of you share these difficulties with existing AR tools and runtime, if some of you are also involved or in related standardization initiatives.
There's a question in chat.
Yeah.
And let me read that off so we can get it. Can you estimate how soon we can get to at least 85% interoperability where end user can seamlessly teleport from world to world with assets and attributes without extra configuration? When is the age of the abstraction to drive and no fine-tune engine?
So I'm not sure to understand well the question. It's written in the chat, right?
It was a private message, sorry. Let me repost this one. This question actually showed up during registration, so maybe it's better handled during the end question and answer session.
Okay.
So there's another one here. A simple question. You mentioned ISO SC9 WG7. What TC?
You know it, Jérôme? On my side, I don't know anything about this work.
Sorry, I don't know the TC behind that. I don't have the answer. So if there is no more question, perhaps we can move to the next part of the presentation.
Leonard, it's Neil. I have my hand up. Okay.
Oh, I'm sorry. Yes, Neil.
Yeah, no problem. So I was just, this is great. I'm looking forward to the next section. I mean, as we kind of consider the kind of the summary you've given, have the ETSI ARF team talked to the OpenXR team that they are thinking about spatial entities? It would be great to have that conversation. Is that already ongoing? Do you know?
No, my knowledge, no. We have many discussions with OGC, some other standardization group, but not with OpenXR.
Okay.
Jérémy, perhaps you can complete.
No, as well. I don't know anything about any link with the Kronos group, but it could be interesting to have more discussion with the OpenXR, as I know we are also working on stuff related to anchors.
That's cool. That would be good to enable. We can talk about that offline. That's awesome. Yeah, thanks.
Sure. For sure, yes. So let's continue on the specification. For that, we consider different kind of definition. So can you move to yes. So the world representation will use different kind of trackable. You know, the trackable is an element of the real world of which features are available on or could be extracted. And it provides also a coordinate reference system in which a pose can be expressed. Different kind of trackable exist today. Perhaps it's not enough exhaustive, but you can use simple fiducial or QR code trackable. This black on white 2D marker. You can use a 2D image. That's a very efficient trackable that provide you high accuracy, but of course it's limited to a specific and a very small area. You can use some mesh trackable. So just by providing the mesh, the system will be able to estimate the pose according, for example, to a depth sensor or just a camera, knowing the mesh of a specific object in the real scene. Or it could be a CAD representation model for industry application. And of course, what is widely used is the map, 3D map. This is a point cloud. On each point cloud, of course, you have different kind of metadata. We speak about the feature and the descriptor attached to each of these 3D points. But you will generally need also some way to have a keyframe retrieval and to have description of keyframe and many other kind of metadata behind this. This is what we call this map trackable. But of course, here we are speaking about vision sensor, but you can imagine to have different kind of other sensors, such as radio sensor, and you can imagine to have radio trackable associated to this sensor, which are wideband trackable. But you can also use some microphone, knowing, for example, the position of the different sound sources. You can imagine, for example, to estimate a position in the real world. And what's happened, of course, today is that you have sometimes new way to represent this real world. And of course, it's this network, neural networks that can directly represent the real world. It's an abstract representation, but there is more and more technologies that are based on these neural networks to finally provide a way to estimate the pose, to represent the real world, and to be able to estimate the pose of a camera or other kind of sensors. Next slide, please. So we make a distinction with the geo-trackable, because geo-trackable do not have a representation, physical representation on the real world, but it provides a position orientation on Earth in a geodetic referential. This is very interesting because finally, thanks to this geo-trackable, you are able to position in relation to these geodetic referentials the different kind of other trackable, and we will show that just after. So on another point is that most of the time, what you need is to estimate the pose in a Cartesian referential according to an object. But sometimes, and this is what is proposed by OGC on OpenAI Cloud, is to provide the pose in reference to the geodetic system. So just to provide a pose in relation to the Earth, in fact. This is a common way, finally, to express a position on an orientation in the real space. So the fact to use the geo-trackable in combination with the trackable is very useful. We will show that just after. Next slide. So yes, trackable is used by vision engine to be able to estimate the pose. And what we introduce also is what we call world encore. World encore is simply a fixed reposition orientation in the real world. And what is interesting is that you will be able to attach some virtual content to this world encore. Yes, next slide. And finally, we have the augmented reality asset. This is a virtual content that will be displayed to the end user at the end. So this AI asset will be attached to world encore, and we will position according to this world encore. And of course, you can imagine different kind of content, such as 3D model, images, video, text, sound sources, and much more. So what are the main elements of a world representation are the trackable with the geo-trackable, the world encore, and the AI assets. Next. How to organize all these elements. These elements will be organized spatially. So you will be able to define some 3D transform between world encores and AI assets, or between world encores and trackable. And this is how you will be able to spatially organize all these elements relatively to the real world. Next, please. And to organize them, one of the way we have chosen to organize them is a graph structure, and more specifically a tree structure. Why? Because this is what is used to represent a virtual environment, a virtual scene. You use a scene graph. And finally, this is well known by the community, and this is well adapted, well suited to represent the different virtual objects in a virtual scene. And so we decide to use exactly the same structure to represent the real world and to organize the different trackable encores and assets, finally, because you will attach some assets to the world encore. And this is what we call the world representation. This world representation is a graph of world encore and trackable, and you are able to attach to the world encore different kind of AI assets. But what is why we have dot for the 3D transform between AI assets and world encore is AI assets are part of the scene graph of the virtual representation. And so you will add some links between AI assets and world encore to link finally the scene graph with your world graph representation. And this is two dissociated representation, the virtual scene and the representation of the real world, and you will be able to combine them together thanks to this link and connection between AI assets and the world encore. So here you have again the trackable that will be used to estimate the pose. And you will be able to express the pose not only in the trackable frame, but also in the different world encore frame. Knowing the 3D transform between the AI assets and the world encore, you will be able to display finally the AI assets at a perfectly positioned in relation to the real world. Next slide, please.
I can go on if you want.
I will let you the floor.
Yeah, okay. So we can move on to some example illustrating the world and the scene graphs. So here is the most basic example of a world graph for creating a small scale experience. So this is a typical example of augmented reality application where we attach a 3D assets to the real world thanks to an image marker. So the world graph here then contains only a fiducial marker definition, and the scene graph contains a 3D model of the lamp that will reference this trackable of the world graph, for example, by using its ID. And a 3D transform by define the spatial relation between the virtual lamp and the trackable. And so as soon as this trackable will be observed by the augmented reality camera, the corresponding asset will be visible by the user. So here is a similar basic example, but this time for defining outdoor augmented reality application. So here we aim to attach virtual information on top of a real building. So the world graph then contains only one geo-trackable that include the positioning information of the building, for example, encoded as GPS coordinates or a geopose. And in the same way, the scene graph contains the virtual asset displayed on top of the building with the reference to the world graph. And so GNSS or visual positioning system can then be used in order to estimate the localization of the user relative to the building in order to accurately position the virtual asset in his field of view. So to continue, here is an indoor example in which we want to localize a user inside the building for different technologies such as image marker, Wi-Fi radio signals, and also as well as the 3D map of the environment. So the scene graph does not need to know the concrete tracking technology that will be used at runtime. It will just have to reference the world anchors of the world graph that will correspond to fixed point within the building. So for example, here the world graph includes one main world anchor for the floor, as well as two world anchors referencing meeting rooms, as we can see on the left. So the interesting aspect of the world graph is that it can allow to define multi-scale experiences and also to address devices that support different kinds of trackables. So in this factory example, trackables and world anchors are linked in a graph to an Earth position for several nodes. So it enables the system to transform a pose from a local Cartesian space to a global geodetic coordinate system. It is then an example of how the world graph can model large-scale environments and multi-scale AR experiences, from the localization of multiple factories in a geodetic coordinate system to the localization of particular elements of machines. So, for example, for assistance scenario, which would rely on image marker-based relocalization in order to really have high accuracy 3D registration between the virtual and the real world. So the world graph is then a common representation of the real world that can be used to deploy several augmented reality applications in the same place. So these AR experiences rely on scene graph that directly reference the world graph. So contrary to other solutions, the representation of the real world only needs to be performed once. So to illustrate this aspect, we use again this building example that includes world anchors that rely on multiple trackables to localize users and particular point of interest in their environment. So one anchor represents the world floors and two anchors represent particular rooms. So based on this world representation, it's then easy to start developing augmented reality experiences. So here we have two examples. On one side, we have an emergency exit scenario that can be created by placing 3D arrows that will reference the main anchors. Then what we can see on the scene graph is that this scene graph will directly reference the world anchor of the world graph. And then we can associate to it the different 3D arrows. And then it's also possible to propose a room occupancy use case where UI panels will be associated to the room anchors. So as we can see in the scene graph, two augmented reality assets showing the occupancy of the rooms are associated to the corresponding world anchors. So one for each room in the world graph. So this is the scene graph that we can see on the bottom right. So at runtime, the world graph and the scene graph will be used to display the augmented reality application to the end user. So if we go back to the augmented reality framework architecture, we have a component named world analysis, which is responsible to estimate the pose of the asset of the scene graph relative to the user. So for each reference element of the world graph, it then needs to extract the corresponding metadata to estimate its pose at runtime. So this is the role of the relocalization information that are provided by the world storage component. So for example, if we want to estimate the pose of this world anchor, we have multiple trackables available to do so, as we can see on the graph. So first, the world storage will filter the compatible trackable based on the capability provided by the world analysis. So for example, all augmented reality runtimes are not able to track any kind of element, such as images, matches, or map. All come with different capabilities. And this is the role of the world storage to filter the compatible ones. And second, the information about the trackable are communicated, such as their type, size, and payload, allowing the world analysis to initialize the corresponding tracking module. And last, the relative transform between each trackable and the requested element of the graph is also communicating, allowing to compute the final pose of this anchor based on estimated pose of the trackable. So if we summarize the process here, so 3D registration aims to estimate the relative pose between the device on the left and the asset on the right. So to do that, we need to compose three transforms. So first, we have on the right the transform between the asset and the world anchor that is included in the scene graph. Second, we have in the middle the relative transform between the trackable and the world anchor contained in the relocalization information. And last, we have the transformation between the device and the trackable, which is estimated by the AR runtime or remote spatial computing platforms. So for example, by detecting an image marker based on an image provided by the camera of the device. So what we have seen on the previous slide is that it's possible to have multiple trackables to compute the pose of a single word anchor. So this is the role of the word analysis to implement how such cases are managed. So multiple approaches can be proposed, such as merging the result obtained from different trackable, or deciding based on the score of confidence attributed to the different types of trackables. So for example, with the most common runtimes today, image-based tracking is known as more reliable as mesh-based tracking, and so then could benefit from an increased confidence score. And so here is the complete process for 3D registration as proposed by the ARF architecture. So it starts from the scene management, which handle the loading the AR scene and interactivity stuffs. So it starts by loading a scene graph and asking the word analysis to estimate the pose of one or multiple elements based on their ID. So the word analysis then asks the relocalization information to estimate the pose of each node of the word storage. And so based on this information and the data coming from different sensors, the word analysis based on an AI runtime or a spatial computing platform will estimate the pose of each node and send the updated pose to the scene management. So the updated scene is then rendered to the user for their device, such as an HMD or a smartphone or a tablet, any device that is able to manage augmented reality. So here were the main concept and example provided by the SDO architecture. So before moving to the available open source implementation, we can have some time again for question and discussion.
At the moment, there is no hands up or questions in either chat or Discord. Oh, here's the chat. Joe.
Yeah. When I see the diagrams on there and I see the little coordinate system diagram that's up, and it seems to be kind of backwards with respect to the GLTF coordinate system. My bane. But how can we explain this when I look at the little coordinate, maybe back one slide, to see how the coordinate system is pointed there? It seems like you've got plus Z pointed backwards with respect to the GLTF coordinate system. And how does this play in with, for example, the Vulkan? How do we handle this? It seems like a simple transform, but it seems like if we're out there in the real and virtual scene trying to put it together, that we got to do a bunch of reorientation. This AR asset up there on the right, it shows plus Z off to the left there. That is not a GLTF asset in its normal coordinate system. Thank you for considering that question.
So I can try to answer, but basically the asset on the right can be a GLTF asset. So we have done I will detail later, but we have done an implementation based on GLTF where we add some information in nodes where we can reference ID of the word graph. And so then basically at runtime, the goal is just to compute the pose of this node based on this data coming from the device and coming from the word storage. So it's not managed directly by the file format or by Vulkan, but it's just about a component, the one that we name word analysis, that will be able to compose these different poses at runtime by just composing matrices, basically. I don't know if you want to complete, Jérôme.
Yes, typically in a rendering engine, what will happen is that, for example, you will be able to use, for example, this anchor as the root of your scene graph. By combining the transform between the anchor and the trackable and the trackable on the device, it will provide you 3 transforms that will help you to move your virtual camera in your virtual scene. Just to align the viewpoint on your virtual scene with the viewpoint on the real scene. So this is how it works. And of course, you will have to adapt the parameter of your virtual camera according to the parameter of your real camera, just to have a perfect alignment. And this is what is done by all at runtime. But here again in GLTF, you will have what you have on the right. So you will manage the IR scene graph. So the different transform between the anchor reference and the IR sets. And the system will provide you the transform to move the virtual camera and to have the correct viewpoint on the virtual scene. I hope it's answered your question.
There may be some confusion on this. Should anybody implied, or should the axis labels XYZ be implied by the colors, or the colors just for convenience and not necessarily implying an XYZ, a specific XYZ?
Oh,
in
yes.
this diagram.
So I think that we need a real standardization about the orientation of the axis between the vision community, the different rendering engines, the different tools to create some 3D models, between the geographic information system community. We have all different kind of orientation on left, right hand, on left hand. But that's very simple to convert the transform from one system to another one. If it's a Cartesian system, that's very simple. So whatever where is the y, the x, y, and z axis, it's quite simple to move from one system to another one.
Thank you.
Couldn't that add a little bit of noise in the transformations though, and kind of increase the complexity of it? Okay.
What kind of noise do you do?
Well, just mask noise in doing for example, that AR asset there, if that's an accurate, if plus Z is going off to the left there as far as it, then if I have to convert that, doesn't it add a little bit of jitter or something in trying to put it in the scene? I guess that's okay. I'm satisfied. Thank you.
I'm not sure to understand, but I guess.
Yes.
There's another question in chat. It's why are room corners not used as anchors?
I can try to answer, but here what we call world anchors are really defined by the one that will, for example, design its augmented reality application, or the one who will describe his building. So it's really driven by the user. It can basically, here for our use case, it was more simple to say, okay, we will need to use the room, so we will place some world anchors inside the rooms. But for example, the corners of the room could be used by trackables. For example, a visual positioning system could rely on, I don't know, corner detection in order to provide a 3D position. But there is really a distinction between the trackable and the anchors that are not really correlated to any feature or descriptor within the real world.
For example, for industrial use case, most of the times they have a BIM model, a building information modeling model. So this BIM model already defines some reference coordinate system for the factory or for different workshops. And what we recommend is to align typically the different world encore with the different reference coordinate system they have defined in their building information modeling. That's a way to ease the alignment finally, because when you want to extract a part of your BIM model, you can directly attach it to the corresponding world encore, and automatically everything will be aligned. So again, it's really driven by the use cases, by what you have already available. Yeah. So could be attached to the corner, it could be attached to the floor. It depends of how you want to design your wall representation, depending on how you want to use it for different kind of application.
Any other questions at this time? Okay, so go ahead and proceed with the next section of the presentation.
Sure. So what we want to highlight as well is that the ISG has also invested time to implement this specification into reusable and open source code. So I will show you the link later, but you will be have access to the slides in order to get these links. But the implementation of this specification can already be found on the ETSI Forge and GitLab. So it's not on GitHub, but it's on the platform managed by ETSI. And so first, we have developed an editor allowing to visually create a world graph with all the metadata describing the world anchors and the trackable of the whole world and the links between them. So this world graph editor is available for the Unity game engine and as well can also be found on the ETSI GitLab. So as an example, if I want to include in the world graph a trackable based on an AirCore cloud anchor, I can just provide the ID retrieved from the Google API and use it as a payload for the trackable in the Unity editor. So what we can see here is that we can load a 3D model of the real environment, for example, a BIM model, in order to accurately place the trackable and anchors according to the real world. So in the same way, we also provide Unity tools to attach objects to the nodes of the world graph, allowing anyone to simultaneously edit the world graph and the scene graph in the SIM tool. So the world storage server that is used can be easily configured, allowing anyone to deploy its own ARF compliant server. So the GitLab also provides generation workflows and associated implementation to deploy your own ARF world storage server based on C# or C++. And we have then developed several world analysis instances in order to demonstrate a full ARF-based use case, including the world representation and the deployment of an AR application on a device. So in this development, the scene management and the rendering part were as well managed for the Unity game engine that could communicate with the world analysis with two different methods. So first, we developed a world analysis that runs locally on the device and that communicate directly with the Unity application. So to do that, we have used AR Foundation, an interface proposed by Unity to leverage augmented reality runtimes such as ARKit on iOS and ARCore on Android. And we'll see with the example that the world analysis and the world storage allow us to manage the difference included in ARKit and ARCore, as they do not support the same trackable. And second, we also demonstrate that a world analysis can also run remotely and be interfaced with the AR application for REST interfaces. So in that context, we have developed a full open API based on the requirements included in the ARF specification and the generation workflow to develop ARF-compliant remote world analysis servers. So two examples have been implemented. I will have the opportunity to show them to you. So one Python simulator was developed by Fraunhofer HHI, and one based on the overview platform developed by Bcom which proposed accurate indoor localization based on computer vision and AI algorithm hosted on the cloud. To illustrate the full pipeline, we used a pretty basic data center maintenance scenario where the goal is to use augmented reality to guide a technician from outside the building to a server room and then to a dedicated equipment. So we then use classic 3D arrows to guide the technician to the room, indicate the equipment to install. We also display security instructions for UI panels, and then we also highlight where these equipment need to be installed. So to do that, we relied on this wall graph on the middle that illustrates different kind of trackables supported by the word analysis implementations. Using more and more accurate trackable, the more we approach to the server room. So we then start with a mesh or geo-trackable, depending on the platform, to locate outside. And then we use a map trackable to locate inside the building. And then we use image trackable to precisely locate the server room and the equipment. So here is the result of this application running on both iOS and Android. So with the word analysis implementation that rely on AR Foundation. So the scene graph and the word graph are exactly the same, but of course the word analysis rely on different types of trackable depending on the platform. So what we can see here, for example, for locating outside, AR Core benefit from something called geospatial that allows an accurate outdoor positioning that we use to implement geo-trackables. And as this feature is not available with ARKit, we did rely on a mesh trackable. So here a car electrical terminal to locate the user outside the building. So indeed, mesh trackable are not available on Android. And when we go inside the building, we switch to map trackables. So maps correspond to regions of the environment that have been previously captured. So on iOS and Android, this refers to what they call spatial anchors that allow the creation of persistent AR content. So the implementation are different on ARKit and ARCore. So ARCore handles anchor based on Google Cloud, while ARKit lets you save the map, including anchors locally, and share it as you want. So both systems are implemented by this version of the word analysis. So as we can see on the end of this video, we then switched to image trackable in order to accurately guide the user to the correct server rack and to the correct equipment. So for example, here we can see that this virtual content displays safety instruction for UI panels as well as guiding instruction. So basically, both applications run exactly the same on both type of devices. So this first word analysis implementation runs locally on the device. But what is interesting with the specification and with the API that have been proposed is that it can also run remotely and communicate with the AR application for REST interfaces. So to do so, you can find on the ETSI GitLab a simulator based on C# and Python that allows to test such features. So it demonstrates how the pose of anchors and trackable can be requested for REST-based APIs and then be streamed continuously to the AR application for WebSockets. So this was developed by Fraunhofer HHI. That's why we can see the logo on the video. So this demonstration comes with the server code generation workflow based on the API, OpenAPI files, allowing anyone to redevelop an ETSI ARF compliant server, for example, based on your own spatial computing platform. And this is what we can see on the video. This is a live version of the simulator in the HHI building with exactly the same use case. Where the virtual content is displayed to guide the user to the data center. And here is the last demo and last version of the word analysis that have been implemented in the context of the ISG. So talking about a spatial computing platform, an example of server has been developed with the Become Overview Air Cloud platform. So Become Overview is a visual positioning system that can run on any network infrastructure. So it consists of a set of services able to map the real environment and locate in 3D air devices such as smartphones, tablets, and AR glasses at a building or at the factory scale. So it's compatible with iOS and Android devices, as well as some AR headsets, such as HoloLens and Lynx. So here the server was developed with C++, and as well you can find the generation workflow based on the OpenAPI on the GitLab, as well if you want to adapt it to your own platform. And as shown, the deployed application is globally the same. It's in a different building, but the concept is exactly similar. So we use arrows to guide the user from outside the building to a specific room and an equipment located inside the building. So the use case here is illustrated in the building of Become. So the video was captured here with an HoloLens, and what we can see is that the solution can cover a multi-story building. To do so, it leverages a different kind of trackables, so we can see some fiducial marker placed at each floor. And there is a global consistency that is maintained with a 3D map trackable in a format that is specific to the overview solution, which can, of course, also be included as a trackable or in the world graph. So if you need more information about Become Overview and this solution, do not hesitate to contact Jérôme, who will be the best to answer any request.
Tracy,
So,
we have a question here.
yeah, if you want.
Yeah. Sorry, this is just a clarification. This is just going back to what Joe and I think Leonard was also talking about earlier. So in your original diagrams from the last section, this is going back to the Z up Y forward question. So your last section, all your diagrams had Z up Y forward. You don't need to go back, it's okay. But in your example, you're using Unity, which is a Y up Z forward environment. So basically what you're saying is whatever your development environment is, whether it be Y up or Z up, whatever it is going to work perfectly okay, regardless of the diagrams that you had in the previous
of course, but
section.
Yeah.
I mean, it's based on the environment you're developing in rather than very, very specific. So it was like an arbitrary thing that you had in your diagrams previously, and it really depends on whatever the development environment implements, whatever they're Z up or Y up, right? And that will just work.
Yeah, depending on what axis is used regarding the up axis, you will need to have some conversion in order to have a consistency between the scene graph and the world graph, of course. Yeah. But this is managed by the word analysis component. If you want to adapt the implementation to, I don't know, another game engine such as Unreal, you will need to manage this kind of conversion of
because Unreal is Z up, right? And Unity is Y up. Yeah.
Exactly.
I was just kind of curious as to what if you had to do anything in these different environments to do like a conversion or anything. I mean, I found in the stuff that I do, you don't. But
this is probably one of the limitations of the open source implementation today. It's basically based on Unity, and we did not do the effort to adapt the solution to another environment. And this is typically something we could address in the future.
Okay, thank you.
Thank you, Tracy. Jérôme, you're muted.
Yes, just again, on your rendering engine, when you receive the post, you just have to multiply it by a 4-4 matrix. That is a good one to transform from one system to another one. So yes, that's very simple. But you have to do it for sure.
Okay, so just to finish, it's almost we're almost finished. So here are all the links to the source code and to the APIs that are available. So you will be able to have access to the slide from what I understood. Basically, this, as I was saying before, this is managed by ETSI. So you have two types of URL: the API on or store on what they call the forge, and the source code with the implementation or store on the what they call their GitLab labs on ETSI as well. So do not hesitate to visit the different pages and see the implementation. And so to finish, just to talk about the next step of the group. So as detailed, the ISG has mainly addressed the problem related to relocalization for IR systems. We've published specification and development of open source solution. So we have also worked on a standard landscape document that map existing virtual worlds standard with the architecture proposed by the ISG. So the goal is to identify in which kind of standards could fulfill the feature of each block. So this document is already available on the IRF portal. And the group is also working more deeply on the representation of the real world for integrating elements related to the appearance and geometry aspect in the graph. So the goal is to simplify authoring and to include interactive behavior at runtime, such as occlusion and physics between virtual and real elements. So this specification that covers some specific reference point of the architecture will also be published soon, so I guess in 1 month or 2. And we have also an ongoing project associated with the group, which name is VUISO, which is funded by the European Commission, which is also working on a virtual world standard landscape, as well as on a recommendation report regarding the future of standardization in domain. So related publication will be available this year as well. And if you want to have more information, you can also contact Christine Perret, which is also involved on the MSF side, and who is managing this project. And so to finish, so do not hesitate to visit the page of the ISG to collect more information. So as I was saying, the slide will be shared as well with a link to the Git repositories. And we are also looking for new contributors within the group. So please contact us if you want to have additional information. And so to conclude, I can say that thanks a lot for your attention, for being there today. And do not hesitate if you have additional questions.
Neil.
Yeah, thank you. Firstly, thank you both for that. Was an awesome presentation. That was really great to get up to speed with the good work you guys are doing. And I think, I mean, I can just see multiple potential collaboration points between what you're doing and some of the work at Kronos. So again, really love to connect those dots and really have that conversation for the benefit of both organizations. That would be great. But we'll definitely follow up with that. And thank you for putting up that kind of the ARF broader diagram. One of the newest working groups at Kronos is a camera working group. Is there? Do you think there may be interest? Should we put that on the mutual discussion agenda too? Is ARF potentially be able to leverage a standardized, hardware level camera API? Or is that out of scope for ARF?
We have worked on the requirements concerning this camera specification, but we do not move to the specification on our side. But yes, you are right. There is a real need for any kind of services, remote services, or for application running locally on the device to get an access to this camera, but also to get an access to the different parameters, what we call intrinsic parameters or calibration parameters, for example, on much more. For example, to get an access to timestamp for each image that are produced by the cameras. So for sure, there is a real need to have a standard on camera side to be able to run any kind of localization algorithm, but not only to be able to recognize objects in the scene, to be able to do some sparse or dense 3D reconstruction. So yes, there is an interest, but to be honest, we work on the requirements, but not yet on the specifications. Perhaps Jérémy, you want to add something else?
No, it's pretty complete. Yeah.
Yeah, but that's good because we are working on the spec. It will be really great to get your requirements. I mean, that would be perfect. Yeah. Yeah. Okay. Cool.
We can share the link. It is available on the IRF website. We will share the link on the requirements.
Yes. Okay. Awesome. Thank you.
Thomas?
Yes, thank you. I mean, I'm a bit interested in like also how we can connect this to the Metaverse Standards Forum, but is there a common membership? Is there a group that should look into this into more details? That's one of the questions. The other one is really about, so do you have indications that the specifications are used in commercial services? And do you get, so where do you get the requirements? Are you getting this from deployments who basically say there is lack, or how is it structured, right? So is there basically a commercial service that like you have on, let's say, GLTF? So there's services and you identify the new extensions are needed to fulfill this. So how is this addressed? So these are the two questions. How can we relate it to the MSF? Is there a working group that should look into this more? And who is there do we have deployments and the requirements? How do they come in?
Maybe I can try to answer the first part of the question regarding the MSF. So since the beginning of the MSF, we have been involved and we have some discussion within the virtual real world integration working group. And so we have also a history of collaboration and discussion with the people from OGC and OpenAir Cloud. So I guess there is a working group when we can already collaborate on this kind of stuff at MSF, and we are still participating sometimes to the meeting of this working group. So I guess everything is okay on that side.
And concerning the requirements, they were based on use cases providing by industrial players, but mainly by end user of AR technology and not by technology provider. So I'm thinking about manufacturing players, but also players in the telecommunication industry, such as Orange and Deutsche Telekom and other. And we collect these use cases. Most of the time, they have always the same requirement. So having a solution running at a large scale, being able to manage only single world representation instead of managing different world representation for different systems they are using in their factory or in their building. Yes, so we start first with use cases collection. And from that, we work on the requirements. And finally, we arrived on this specification mainly based on a tree structure or how we can especially organize different kind of trackable coming from different kind of systems. So unfortunately, there is no technology provider in the group. This is one of the limitations of this group, for sure.
Okay, but is there any service that would be aware of that would rely on the specifications?
Many is the ones that have been presented. So yes, the one providing by Becom and also the integration of the solution from AirKit and AirCore presented by Jérémy.
Yeah.
So I will say that this representation on this specification is working with any kind of existing system. You can easily add as a trackable the trackable, or what is called Encore, providing by AirKit, AirCore, or the kind of technology. So you can imagine to have in your work representation trackable for AirKit, trackable for AirCore, trackable for Microsoft system, and finally, depending on the capability of your device, you will be able to extract as a relocalization information, the good one, to be able to localize. But what is interesting is that whatever the system you will use, you will localize exactly at the same position, because the trackable from AirKit is not specially positioned at the same place as the trackable from AirCore, because most of this trackable or 3D map are referenced according to the original viewpoint when you start to do a mapping, when you start to map the world. So when you are creating a map of your real world with Android, and you do the same thing with iOS, this different map, 3D map, will be positioned in different place. And thanks to this world representation, so the world graph, you will be able to align them and put them in the same reference system. And that's clearly one of the main benefits of this representation. Being able to put all these trackable in the same coordinate system, on a common coordinate system.
Mike, please.
Hi, yeah, just maybe a slightly naive question. So you've got these different world graphs and so on, and I see a lot of graphs and integration of different graphs by common identifiers like UUIDs. And I'm intrigued, like that's a parallel to what we call formal ontologies or semantic technologies, where we use URIs rather than UUIDs, and you have graphs that represent the real world or represent data about the real world. And I know at least some vendors in this space are using formal ontologies to create and integrate different renditions of world views and so on. I just wonder, is that something you see being used in the future or not? Is like more conventional semantic technologies, or is that kind of passed by?
For now, the specification and the open source implementation do not include anything from my knowledge about using ontologies. But on our side at Orange, we have an internal platform for representing digital twin based on ontologies. And so what we have done is that we have performed a mapping between the ETSI ARF concept within a dedicated ontology. So we are able to create what we have demonstrated here, world graph, based on a given ontology. So this is definitely something that can be applied on this specification, yes. But this is not published.
And just to complete, yes, the world graph today is really focusing on localization. So you have the trackable, and trackable are there to be able to localize the devices, or to localize devices in relation to the real world, or object in relation to the device. You have the world anchor. It's just a position in 3D space on which you will attach a virtual content. And as mentioned by Jérémy, we have worked on requirements to add a geometric representation of some elements of the real world. It could be, for example, a mesh that have been reconstructed to manage occlusion, to manage, for example, the physics. But in these requirements that will come very soon, the idea is to add a new kind of object in this world graph. It will be called something like world object. And this world object is a geometric representation, not trackable just to localize, but the geometric representation of the real world. For example, the dense point cloud of an object, an element, or of a scene. And we plan in the requirements to add also this semantic information. For example, if you want to deploy a game, for example, to play ping pong on a table, and you are looking for a table, you will be able to find a 2D object in your environment close to you, on which you will be able to deploy a ping pong game on a plane on top of a table, for example. So this will come very soon, and the requirements will be soon public. We have not yet worked on the specification on this aspect, but yeah, this is the idea to extend this world graph, not only for localization, but also to keep a geometric representation, but geometric and semantic representation of the real world that can be used by different kind of applications.
Okay, thank you. We need to
Thank
move
you.
on at the end of our session. Just now for the wrap up. First off, in the chat and also on the screen, it's a link to our survey. Please fill it out. Include anything that you find that was good and anything that we can work on to improve. All that would be really good for us to know. Second, please consider joining the forum. Your membership means a lot to us. Of course, those who are paid mean even more to an extent, but everybody is welcome here. And once you're joined, you're all into the same category. And then lastly on this, if you are an SDO or if you know of an SDO that has some recent work in anything metaverse related, you're welcome to fill out the form. The link is in chat for this. So want to make sure we thank today's presenters, Jérôme Lacoche from Orange, Jérémy Lacoche from Orange, and Jérôme Royan from BCom. Also, MSF President Neil Trevitt and Executive Director Emily Stearns. Technical support today was provided by Lisi Artson and Jeff Phillips. The special SDO session producers Thomas Stockheimer, Christine Perret, and Leonard Daly. If you have any additional questions or comments, please use the Discord for the continuing conversation. Thank you very much.